whole
Did you already sign in? Sign in? Yeah. You guys start passing it that way. All right, you ready to start?
All right. And
I think he just said that he can't. Unfortunately, yeah, he has to PhD.
sorry, we forgot to do one thing.
No problem. So while they're getting set up, just want to mention there should be a sign-in sheet floating around. Please tap it around. If you already signed it, just hand it to the next person. And if you didn't, please put your name on it.
Maybe the form can go after that.
Are we good? Go. Okay. So welcome everyone to the Technology Seminar Series. Sorry, I know the pizza arrived a little bit late, so we're getting a slightly later than normal start, but that's not too much of a problem. Again, the sign-in sheet is passing around. Please do sign in. Today's speaker is Simone Marini, and he is a research investigator at DCMB, and he's going to talk to us about multi-omics integration for precision medicine.
All right. Hello, everyone. Welcome. Thank you much for your introduction. So let's start. Okay. So precision medicine. The concept of precision medicine is not new. It's somehow intuitive. The fact that one treatment doesn't fit all the patients suffering from the same disease. We can see it from two different angles. One is that the patients may respond in a different way to the same treatment, or we need different treatments to get the same outcome, the same response from with the different from different patients. So this idea may come from the fact that traditionally we categorize diseases based on symptoms, based on what we can measure, but of course the very same disease may present different symptoms. And the truth is that there's probably some molecular mechanism that is aberrant from the norm, and that can be different. They can be in a spectrum of diseases. These also overlaps with, for example, drug repurposing, drug repositioning, in terms of shared molecular mechanisms or aberrations. This is just an example. This is a paper showing that people taking, for any medical reason, antagonists of this beta-2 adrenal receptor have been found to be less at risk to get the Parkinson's disease, because there's a common molecular mechanism. Now, the problem is that we don't know the molecular mechanism. Maybe we cannot even measure them. Anyway, starting with that said, starting from this, we could think at precision oncology as the perfect arena to play precision medicine, because cancers are categorized, are classified, maybe on what we can measure, what we know about them. For example, they are classified based on histology, but we know that deep down, maybe the same kind of cancer classified in the same way can be, in truth, different because of different underlying molecular mechanisms due to mutations. So, how does precision oncology applies? Well, it depends. Here I am bringing the data from this trial, where about 200 patients were enrolled, and more or less equally they were split between precision oncology and a traditional approach, and the results were apparently not spectacular. Okay, there was not a very big difference between the precision medicine application and the traditional treatment. Also, only less than half of the patients could be enrolled, could be, how can I say, they could be destined to having a precision oncology treatment. This is another trial where we start with about 700 patients, but then when we look to find these known molecular aberrations that can trigger the precision oncology treatment, the number of patients that can have the treatment drops down considerably. Now, why is this? Well, it's because if we look for something we already know from literature, if we look for pre-identified molecular signatures in cancer, we are not assured that they are common. Okay, maybe we can pin down a specific aberration which we know will respond to a specific treatment, but it's very rare. And to test the outcomes of a precision medicine treatment starting from these premises, we will need large cohorts. All right, so here I'm talking about a different approach. So instead of looking through the literature and find these molecular signatures, we can try to find similar patients. The assumption here is that similar patient will respond similarly to the same treatment, which is in terms of data science clustering. We cluster patients that are similar, and this is the base of precision medicine. In order to cluster patients that are similar, we need to define a similarity. Okay, and so we will maybe discover signatures instead of using pre-identified ones. Now, why not use multi-omics? So we are finding similarities between unknown patients, and we are using all the data that we can gather. Now, we have a lot of different heterogeneous data we can measure on patients. We have genomics, metabolomics, transcriptome, proteomics. We have blood tests, clinical variables, our electronic health record. We have imaging. Okay. So we can put all together and cluster similar patients to see if these clusters correspond to really to groups that are responding in the same way to the treatment or not. So the way we do that is using direct information, something that we measure from the patients. This is just a toy example. So I have a certain patient, and this patient represents a sample. Now, I measure we're talking about cancer, so let's say that we sequence the sample from the patient, and we can pinpoint which genes are mutated. So this is like oversimplifying, but just to give you an idea. So each patient can then be represented by a vector, right? A binary vector. Each element of the vector corresponds to a specific gene, and I'm just checking if that gene is mutated or not. I'm not considering how many mutations. I'm not weighting the mutation. Just putting a 1 if I find a mutated gene. All right. So this is direct. If I had 10 patients, I would have 10 lines, okay, 10 binary vectors. I can cluster them. Or I could apply, for example, intuitively Euclidean distance and find a similarity between the patient. Find a matrix that is squared patient number by patient number, and find how a patient is close to another.
So in this exercise, you're looking at sort of a predefined set of known genes, right? Because
It could,
cancer or
it could be. This is just an example.
Okay.
If I sequence all the genes, I could look at all the genes.
Sure.
I could genotype. I could, but well, that's really general. Okay, it's not important so far. But interesting thing is that usually we don't know just what we measure on the patient. We have other forms of knowledge, other information, which are relevant but not direct, not directly measured on a patient. What I mean by indirect information, I mean, but what can I find in literature? What can I find on the databases? Which kind of information I can drag out of decades of biology and medicine? We have ontologies such as the gene ontology, the disease ontology. We have databases connecting genes and diseases like this GeneApp. We have protein databases, protein interaction databases, gene interaction databases, and so forth. Now, all this information is usually ignored, right? I cluster only based on what I found in my patient. This indirect information represents the relations. It can be seen as representing the relations between the features that I measure on the patient. Practical example. Here I have the patient, okay, and here are the mutated genes. Now I take the first gene and I call it gene J, and from literature I can check out which genes here, which of the genes, other genes here, are interacting with the gene. And okay, the gene is interacting with itself and with this other. Now, I cannot intuitively plug in this information here, right? Because it will be, if I just oppose this vector to this other vector, I will find that the features are repeated equally for all the patients. The information is useless. So what I'm proposing here, what I'm presenting here, is a method that will cluster the patient, that will measure the similarity among the patients, and will be based on both the direct information that I traditionally get and the indirect information that I can mine out databases and knowledge bases and so forth. I want to blend all together in a model that will output a measure of patient similarity. Out of that, I can get the clusters and of similar patients.
So what do you mean by interacting genes?
Okay, so genes, they can be considered interacting by a different set of rules. For example, co-expression. Two genes co-express, and then we say they interact. Another way is two genes code for proteins. The proteins interact, they bind to each other. Then I assume that I define the two genes as interact. Now there's plenty of variety in how can I define interacting genes, and this is reflected in a variety of databases and rules. And the different databases to define interacting genes might even provide you a score or a measure of the certainty of the strength of the interaction that can go from, for example, oh, this interaction has been predicted by an algorithm, to multiple experiments by independent teams, targeted experiments prove that this co-expression is present and we're pretty sure of it. And maybe in the middle, there is a co-expression that is the zoomed out of high throughput experiments. Okay.
But in practice, like in string, every interaction has a score from 0 to 100.
That very much depends on how you're measuring it. Then you can rescale it between 0 to 1 if you want.
Okay, 0 to 1, whatever.
Yeah.
But your interactions is binary.
the confidence of the interaction, the fact that the interaction is real, is not. Plus, what if I measure co-expression, okay? Then I'm not necessarily forced to binarize it. The co-expression can be strong or can be weak. There can be a little bit of it, there can be a lot of it. Same goes for protein bindings. You can binarize protein bindings and say that proteins bind or not, or you can measure protein affinity. Okay, we're diverging, guys. Can I go on and later we can discuss about it?
I was just going to say, what you were showing was just a toy example.
Yes. Okay. Thank you. Appreciate it. We can discuss more later. Let me go on. Now, I can do supervised learning if I have a label attached to each sample, which can be a class, or it can be a continuous value. In that case, I would do regression with a class with a classification. But that is not what I'm presenting here. Okay. What I'm presenting here is unsupervised learning, so clustering. Of course, we need ground truth or validation to prove that the clusters that we find are meaningful. But if we are going to find the clusters, we don't know from the beginning, we don't know how they are distributed. We are discovering stuff, we are discovering signature, we are discovering groups of similar patients. So this is not supervised learning. Now, from the toy example, let's go to a practical one. Now, I can get a data set, patients from TCGA, patients suffering from acute myeloid leukemia, and here I have the direct information that have been measured on these patients. So I have clinical data, patients, the samples from the patients, they have mutations, and I can also measure the gene expression profile. Now, I could measure similarity just with this, and I could measure similarity just running a similarity measure on all the possible pairs of this patient. I could use any distance. I could use Euclidean distance, I could use Jacquard distance. I just have to set the rule. But what about the indirect information? Well, here is the direct information that I'm using here. So the information on the TCGA, then I designed this algorithm which is a way to weight the deleteriousness of the single nucleotide variants. So instead of saying, this patient has this single nucleotide variant, I can say, this patient has this single nucleotide variant, which I suppose to be this much or this much or this much dangerous. It's just a way. I could have not used it in case, but I decided to. And then I can plug in gene interactions, pathways, and so forth from other databases, information that I can find freely online. They have the API, you can write scripts, download, filter, and you go. Now, wouldn't it be nice to put everything, direct and indirect information, in one big matrix? Yes, this is exactly what I'm doing here. So this matrix is pretty big. Here is the number of columns, number of rows. It's square matrix. It is a block matrix, and each block here is representing a data source. It is symmetrical. So, for example, I have the clinical data and the patient from TCGA, and I put them here. It's a relational matrix. So, it's filled with the relations between the rows and the columns. So the relation between mutations and patient is, for each patient, I have, if it's binary, for example, I would have a 1 if the mutation is present in the patient. But in these cases, there's a weight applied. Or if a gene is interacting with another gene, then I would have 1 or a weighted number in the corresponding element of this block connecting genes and genes, and so forth. This matrix is extremely sparse. Extremely sparse not just because whole blocks are empty, but even the blocks that are not are sparse. Okay, put some numbers here, but the sparseness is maybe sometimes over 90% in some blocks. Okay, now once we have this matrix put together, here is the proposed approach to integrate direct and indirect information and extract the latent features. So we go for matrix factorization, pre-factorization. So here we have the initial matrix, and well, if I let the machine crunch the numbers for a while, I can come up with 3 other matrices, actually 2 other matrices, G, S, and G transpose, that multiplied together will give me back this initial matrix. So you note here that the diagonal is empty. This is for technical reasons. So this matrix, this big matrix, has been split into 2, and the blocks on the diagonal are filling here another matrix which has the same dimension as this one. And this one is the mention I showed before, but the elements on the diagonal are gone. Okay, they're moved here. So to put it simply, these matrices are smaller. Okay, so the size on the rows is the same. The number of columns is way smaller, right? So if I can factorize the information I have here into 3 different matrices that are smaller, it means that I am in principle filtering out all the noise and keeping only the useful information. If I multiply this by this by this, and they are smaller than this one, and if I multiply them together and I get a matrix which is almost exactly identical to this one, it means that I captured the information in the latent features that are here. So why I'm doing all this is because I want the latent features, and I will come back to this in a second.
So is this eigen decomposition?
Is this, sorry?
Eigen decomposition?
It's non-negative matrix factorization. It's not based on, you mean eigenvalues?
Okay, no.
I didn't get exactly the word you were saying. Well, anyway, it's non-negative matrix factorization, 3 factorization. Now, this factorization is driven also by constraints from this matrix. So I'm trying to reconstruct a matrix that is representing relations between different elements because the diagonal is empty. So on the diagonal I have the relation between the same kind of element, like gene and gene, pathway, mutation and mutation, and so forth. Okay, I'm reconstructing this matrix which is without them, but they are here, and they drive as constraint the factorization here. Now, I'm doing this because in the latent features here, I will find theoretically embedded all the information of all these different data types and data sources that I cram together. So this is the difference between this method and, for example, a normal non-negative matrix factorization, which would have only 2 matrices here and should not have this. Okay, then hopefully the latent features will have embedded all the info. Besides embedding the information that I extracted from the patients, will carry patterns from the databases and the external indirect information that I plug into. So how can I be so sure? How can I see if it works or not? Well, one way is to simulate. So if we simulate, we know the ground truth. Something that, of course, doesn't happen in reality. We know the ground truth. So, for example, here I take 5 patients out of the 200 patients, and I use them to simulate 40 patients, pseudo patients, each. So in other words, I create 5 artificial clusters made of 40 patients each. How do I simulate patients? Well, I just put dirt on the data. So I can use noise, I can make data more noisy, or I can remove some data. I can add missingness, so to speak. So I can take 5 patients, and for each of the patient, I add some noise, I remove some data, and so forth. And this way, I create 5 clusters. Now, I don't tell my algorithm the ground truth. This is unsupervised learning. I run it, and I check how it goes. So, for example, we have 200 simulated patients, right? So this is a similarity matrix. This matrix is telling me which patient is similar to each other, and this is the ground truth. So we have 5 clusters out of 5 patients, 1, 2, 3, 4, 5, that I know from the beginning that they are coming from the same source, so they should be all similar. They should be all clustered together, and the others should have a similarity of 0. It should be different. Now let's say I can run my method, not necessarily with all the matrix factorization that I described before. I can run any method that will output a similarity matrix. Once I have the similarity matrix from the method, I can compare it with the ground truth and see how good the clustering was, how good the similarity measure did work. So in this case, if this is my result, I'm kind of happy because the distance measure reconstructed the clusters, but I'm less happy here because here there are some false positives. There are similarities which shouldn't be, okay? And I can subtract, I can measure the mean absolute error out of all the elements of this matrix and have a general measure of how the matrices are similar. And this is exactly what I did, not just with the method for data integration that I described before, but also with other similarity methods. So we can run Euclidean distance, for example, on the raw data. We can run a PCA on the raw data and then calculate Euclidean distance on the PCA elements. We can use deep belief networks, which are a deep learning algorithm. And we can run group factor analysis, which is another factorization technique, very similar to the one that I discussed, but not considering the external, the indirect information. Okay, so here we are. Here we have the 5 methods applied, and for each method there are these 25 little squares. So each square is a scenario obtained by adding noise and removing data. So here we have a growing percentage of missing data to simulate the patients, and here we have a growing percentage of growing amount of noise. This is measured with a percentage. I will not bother you with too many details. Anyway, here is very simple, here is very hard. And as we can see, these two, how can I say, more fancy method are not working very well. The color represents the mean absolute error, and the methods that are more simple, such as calculating the Euclidean distance on the PCA or directly on the data, are working better. But still, the method that I showed is consistently working better in this simulation. The mean absolute error is in almost all the noise and missing data scenarios less than 0.05. Also, we can see that other methods are, for example, the deep belief network is suffering a lot from missingness, but not much from noise. Okay, so very good. Apparently, integrating indirect information is useful to find real distances, or to find patient distances in clusters. But another way to show that the clustering makes sense is to do the clustering and then use some information that was not included in the clustering process to validate the clusters. So, to put it simple, in this data we don't have information about the treatment, okay, for this patient. But we have information about their survival. So we know which patients were still alive after 5 years. We know the ones that died and when they died. And the survival is basically the main descriptor of, let's put it brutally, how bad the cancer is. Okay? The favorable or unfavorable outcome of the cancer can be seen as the survival time. Now, here let's remove the survival. Let's remove this information. Let's run the algorithm. Let's find the cluster and let's see if the clusters are different in terms of survival. If they are, and of course they are, otherwise I wouldn't present these results, they are meaningful. Okay. So these are the survival curves for the 5 methods applied to the same data without the survival time. 2 clusters for each method, and the method that I'm proposing here is the only one where the survival curves of the 2 clusters are distinct. So without knowing it, just by grouping together similar patients, this algorithm found a cluster with a more favorable outcome and a cluster with a more negative outcome. It's important to see that all the other methods failed. All the other methods, they present curves that are more or less superimposed. I can measure the p-value. The only significant p-value is here with the method that I presented, and is about 0.01. So, let me check the time. Okay. Wrapping up, I presented a patient similarity calculation approach that exploits both direct and indirect information. The data structure is conserved. What I mean by saying so is that, remember this matrix? When I put my data inside this matrix, besides some basic linear scaling, I'm not talking about normalization, but just linear scaling, I am not altering the data as I found them in the databases. The data structure is respected, nothing is compressed, nothing is particularly elaborated or put together. It's built for sparse heterogeneous data, and it can be exploited in theory for other problems, which I will illustrate in a second. Another thing that I want to point out, and I mentioned this when I explained this method to medical doctors especially, what we are doing here, finding the patient similarity, is the machine learning or calculation equivalent of a very human thought process, which happens every time a patient steps into the doctor's office, showing the blood test result, describing the symptoms, and the doctor goes back in her mind and even unconsciously pairs this new patient with what she already saw, what she already know, with the patient she had treated in the past. This works for diagnosis, this works for like finding the right treatment. And of course, if it's a human thought process is subject to biases. We know, for example, that more recent experience are affecting our decisions more than experiences that we had in the past. But this method doesn't have this kind of human biases. All the patients are like considered equally. There's no timeline. Although, of course, there are other problems. Okay, there are maybe other biases, but not the human ones. Okay, so but modifying this approach a little bit, we can get a lot of. We can apply it to a lot of different problems. So here is another application of basically the same principles of putting together external, not directly related information with what you measure. So in this case, it's protease protein target pairs prediction. Now, proteases are protein, okay, not proteins, and they have some specific targets. And when they find the target, they cleave it, they cut it. Okay. This problem in bioinformatics is very well known. The first algorithms trying to predict protease and protease targets were deployed 15 years ago, more or less. And yeah, what happens? It happens that some proteases are very well studied, while others are not. There's not an equal distribution of the human effort in studying proteases because some are more interesting than others. So for example, you all were aware of CRISPR technology. CRISPR is CRISPR-Cas9. Cas9 stands for caspase-9. Caspase is a protease. Okay. So caspase family is very well known, but there are others that are not. And this creates a sort of imbalance in the predicting algorithm, which are tilted towards predicting targets for the superstar proteases. And by applying this method, I elaborated algorithm that can predict a range of targets for proteases, for a range of proteases that is way wider than state-of-the-art algorithms. Most of the state-of-the-art algorithms are predicting, maybe they have a different model to be trained for each protease, or maybe they work for protease families, or maybe they work for target families. But with this approach, I could have a truly general model working, predicting targets for any protease, and most importantly, it works better than other state-of-the-art algorithms, even on their specific target sets. Another thing that is possible to do by extending the similarity/clustering method that I presented here is here calculating, predicting gene-gene interactions, co-expressions in this case, predicting gene-gene co-expressions without knowing expression data. So this is, personally, I think this is cool because when you want to zoom gene-gene interactions, of course you need gene-gene expression. If you want to measure gene-gene co-expression, how could you do it without the expression data? Well, with this method. So in this case, we have a data set of patients suffering from myelodysplastic syndromes, and for them, we have the single nucleotide variants measured, but not the gene expression. Okay, but we have gene. We know that there are gene-gene interactions, that there are domain-domain interactions, that there are protein-protein interactions, and we know that domains belong to proteins. The proteins are encoded by genes and so forth. So we can blend again all together, find latent features describing genes, and using these features to find candidate gene interactions. So in this case, I'm not looking for the similarity of a gene with all the other genes. I'm just looking the single gene-gene pair, and I take the ones that have top similarity, and I claim that they probably are co-expressing. Okay, I claim that. How can I prove it? Well, of course, I can use, for example, this database string, which was not used in the process, and I can see that this independent source of information is confirming that almost half of the candidate interaction are indeed interacting, and of them, more than half have a score that the same database defines as high confidence. Another way is to take external data sets. Okay, let's go to Geo and look for MDS data sets that have controls and gene expression. Now, since these 320 candidate interactions come from cases only, I expect some of them to be interactions that happens in any bone marrow cell, including the healthy ones. But some of them, I thought, they should be present, they should be typical, they should be a signature of myelodysplastic syndrome. We mine them out of the mutations, so they should be there. Are they? Well, yes, some of them. Okay, so I can see if the co-expressions are significantly different between cases and controls, and I find in the first dataset, which is the smallest, 24, 34 in the second dataset, and 40 in the third dataset, and in total there are 83 gene-gene interactions that are differentially expressed, and so this indicates that they probably really belong to aberrations of the myelodysplastic syndromes. 31 of them are present in 2 sets, and 14 of them are present in all the 3 sets. Okay, here I conclude. So this algorithm is there. It's on GitLab. You can download. You can use it. You have me here. So write me for any question. If you want to apply to your data, I'll be happy to talk with you to tailor it to your needs. And of course, I cannot conclude without thanking the several people behind all these projects. My colleagues and friends back at the University of Pavia in Italy, University of Arizona, here at UMICH at the ECE, Kyoto University Bioinformatics Center, and of course the Lee Lab, which is my lab, for the support, starting criticism and help. Thank you.
Yes, so for the data structure that you used for size, I wonder if you do the like bigger size and a smaller size, will the result be make a significant difference?
That's an excellent question. Now, unfortunately, I cannot answer right now because when we reached the results, we were in a rush to publish it. But I am working on it, and it will be interesting to measure not on one data set and one problem, but over this wide spectrum of problems, how adding each data source is influencing the result. And I will definitely do it in the due time.
And also even the same size, that information, if they are different, there could also.
Absolutely. So one question without a correct answer is, how do you decide the size of the latent features? So for some of this work, we used just a fixed size that was reasonable. For other, for example, for the protease protein prediction problem, since it was supervised in that case, we did a cross-validation on a training set to find the optimal size. There are some indexes that describe the sparsity of the matrix compared to the rank that you can measure. In literature, you can find a lot of different approaches to define the size of the latent features. But unless you go for an empirical approach which implies supervised learning, there's no straight answer. My take as an engineer is, if it works, you're happy. If it doesn't, try with other sizes. But again, we didn't, I don't want to be misunderstood. When we didn't, for example, for the patient similarity one, we used a specific method to define the size of the latent features that is based on the rank of the blocks divided by a number which is related to the non-zero element, so the sparseness. But once we decide to go with it, we went with it. We didn't try different sizes and then keep the best. Okay, we just choose one, and also because these calculations are can take time. They can be very big matrices. So that was the strategy that we followed. Yes.
You said early on that you did not have any treatment information on this.
We didn't plug them in.
Yeah, I'm wondering why you excluded that. Because with that, couldn't you use this for medication dosing?
Absolutely, absolutely. This has been done with a similar method, although it was not exactly this one. But I was not in charge of getting this. So I basically work with what I've been given. And honestly, I should go and check if the treatment information is present or not. I don't know, but it's a good question. I will definitely work on a problem which is to cluster and then check the treatment later, maybe instead of survival, for example, to find similarities and then see how they match with the treatments and so forth. Yes.
How do you actually assign the indirect information?
Define assign. Like
you've got to be putting it in your table. You said
yes.
You're using it, right?
Yes.
So how do you decide which indirect information goes to which patient?
Oh, I don't decide which direct information goes to which patient.
Indirect.
Which indirect information goes to which patient. For example, I cannot measure pathway interactions, pathways in patients. Or maybe I can, but I choose not to. And so it's empty. So anyway, you have to make arbitrary decisions to how to represent the data. So, for example, the gene interactions are not attributed to patients. They have their own block. They are not put into patients. But which patient has which gene mutated is here. So, but that's direct. I hope I answered your question. So the data sources can be both direct and indirect. Okay. So if I'm talking about pathways, let's say pathways. Okay. Here we didn't put anything for the pathways, but we could have. We could have, for example, choose to say, look, we check the mutated genes for each patient, and we sum the number of mutated genes that a patient has in a specific pathway and put that information in.
So then that information is, by definition, highly correlated with what you
Yes, and it would sound weird to me, so we did not do that, but we could have.
Yeah, but so you could just end up acting like weighting factors for which thing.
Yes, that could be, and this is one more reason why it would be very interesting to try to take away these blocks one by one and see how the result is modified, or try different combination. The point is it will take time, and I'm working on several other projects, but I will do it. Thank you for
Any last questions?
please.
Just out of curiosity,
Yes.
in your simulated data, how different were the 5 patients?
Right. So we made sure that the Euclidean distance was higher between all of them, between all the possible combination of them, was higher than the average distance of that patient from them. But in this way, we actually helped any similarity measure based on Euclidean distance, and in fact, Euclidean distance on the data and on the PCA, they work better than deep learning. Okay, so I think that's why. That's one of the reasons.
Any other questions?
In page 17, how
Yes.
come your matrix S is not symmetric, but G is symmetric?
What? S is not symmetric. Yes, S is not.
So then how comes the dot product of the green matrix is symmetric?
The dot product is
So
not.
because R is symmetric.
Okay, wait. This is symmetric.
Yes.
Okay.
G is not symmetric.
G is diagonal. Is block diagonal.
You said the number of columns is smaller than R. Then G.
Yes, it's still block diagonal.
So G is square or not?
No, G is not square.
But it's diagonal.
It's block diagonal.
Okay, block diagonal.
Yes.
S is.
Yes.
Is
You can if you have a matrix which is a 10 by 5. Okay. Can you see it's block diagonal?
The first 5 rows are.
No, that's block diagonal. It's different from diagonal, right? Of course, it couldn't be diagonal, but can be block diagonal. Maybe later I can show you the data, or we can discuss this. All right.
Thank you.